All right, guys, I wanted to provide a walkthrough, I guess you could say, of the notes for the remainder of what is chapter 15 from the textbook. Last week we talked about what sound is, how frequency is proportional or is the same as the pitch of the note being played, or how amplitude is the same as your volume, or how loud that little that note that's being played is going to be. This week we're going to talk about how sound itself, now that we know what it is and how to describe it, can actually change. We hear this all the time, even if it is something that you're not normally thinking of when you hear it, but you'll definitely know it. So changes in sound, or the Doppler effect, is what we're going to be talking about. This is the remainder of chapter 15. If you're looking in the textbook at any point over these next couple of weeks, this can be found on page 407. It's the second half of chapter 15, section 1. So here we go. I'll try to make this quick. Not all sounds, obviously, are going to be identical to one another. You're going to have a lot of things that can change. We should already know that sound is just a vibration. It's nothing fancy. It's air particles, or it is particles in the water, or particles in land, in the ground, colliding with one another. It's a vibration that travels from object to object. The closer those particles are in the medium, the density of the medium will determine how quickly that sound can travel outward from point A to point B. We know that the pitch of a sound wave is determined by the frequency, and how loud it is should be determined by the amplitude, how much energy was put into it. It's why you see in your cars, if you look at the speakers of your car, if you turn the volume all the way up, you'll actually see the speaker moving forward and backwards. It's increasing the amplitude of each of those little vibrations, compressions in the air that it's generating, and that's what makes it louder. So we've talked about all of these factors. What we're now going to talk about is how it's going to be able to change based on something very specific. The 420 hertz tuning fork will not always produce a sound of 420 hertz. It will make that sound, I'm sorry, but we will not always perceive that sound to be 420 hertz. If the object is stationary, not moving, not going anywhere, 420 hertz is 420 hertz. However, you can hear a different noise being produced, a different pitch, a different tone, if the object is moving forward and backwards. That perceived sound, what you hear, not what is produced by the tuning fork or the machine making the music or whatever it is, what you hear can have a slightly different frequency, and that's got to do, obviously, with everything we're going to talk about right now. This is what we refer to the Doppler effect as. So the Doppler effect is that ability to have what you hear be different than what is actually being produced. I've got two links here that I want you guys to check out. The first one you probably don't need to check out. This is just if you're confused on what it is Mr. Willis is talking about in terms of sound changing. It's a train passing someone at a station. I think it's in England because of the accent from the loudspeakers. Not important, but you can hear the sound the train is producing change as it approaches you and then passes you. It's the same thing you notice with I don't know, what am I thinking of? Fire trucks, ambulances, any of those things, you've definitely noticed it before. Even just cars on the highway, you've heard that sound. So check it out if you're not familiar with it. It's like 20 seconds or something silly. The one that I do want you to check out for sure is this video right here. The Doppler effect from two different perspectives. It's I think a video a couple of high school kids made. And I'll have it linked at the bottom of this YouTube video in the information section. But in the video, it shows two different perspectives. It's a kid sitting in a car playing a trumpet, plays the exact same note on the trumpet the entire time over a period of about 10 seconds as they're driving down the road. And then the second perspective is a kid standing on the side of the road, listening to the exact same note being played by the trumpet. And as the trumpet goes by, you'll be able to notice that from your perceived, I guess you could say, vantage point, standing on the side of the road, you notice a change in the sound, but the person in the car doesn't. The person in the car, moving at the same speed as the sound waves that they made, continue moving, continue hearing the same pitch. There's no Doppler effect that occurs. It's this change in perception that the Doppler effect is. So More specifics on that, the exact definition, it's a change in frequency for an observer when that frequency or the observer, doesn't matter, the source or the observer are moving relative to the source of the sound. The frequency being produced itself doesn't change, but what you hear changes because it's moving with or away from that particular object. The more relative motion that there is between the source of sound, this is an important one, the more relative motion that there is between the source of sound and the observer, the greater the Doppler shift is going to be. So if you're not moving very quickly, you're not going to notice a very large Doppler shift. If you are moving incredibly quickly, it will be a much larger Doppler shift. So if this ambulance was sitting right here, not going anywhere, but someone decided to screw around and turn on the siren, those sound waves would travel outward. There would be a series of compressions that leave that source in order to make that note. If you've got a 420 hertz, let's say, frequency, you've got 420 compressions being produced by that speaker every second. That's what that frequency means. It's not obviously spaced out this much. But let's say we hit pause in reality and looked at those compressions. This is what it would look like. Now, what you'll notice with this is that if the object is moving to the right, in this case, if the object is moving to the right, there's going to be two things that happen. When it produced this particular sound wave all the way out here on the edge, it was actually right here in the middle of that circle. When it produced this next sound wave, it had moved over a little bit to the right. When it produced this sound wave, it moved over a little bit more to the right. And as it moves to the right, the distance from crest to crest, from compression to compression, gets smaller. If you were to hit the brakes, then that distance would go back to the distance that it should be, and all of these should have the exact same wavelength, therefore the same frequency. But because it's moving, the distance from crest to crest actually winds up getting smaller in the direction it's moving, and you'll notice it winds up getting much more spaced out in the direction that it's moving away from. So your wavelength behind you appears to increase. And that's why in those videos on the last slide with the cars driving past or the trumpet driving past, you would have noticed a much higher pitch as the car approaches you, and then as it leaves, a much lower pitch. High pitch because it's a high frequency, low pitch as it left because it's a lower frequency, it's a longer wavelength. And here's another diagram where you'd be able to see that, right? As it approaches you, you get this series of waves that appear to have a much higher frequency, much shorter wavelengths approaching you. So this would be a much higher pitch. This would be a higher note. So I'll put a little H there. This is a higher note. And then over here where you get the longer wavelengths, because that ambulance, when it produced this note or this wave, is moving further away from when it produced the next one, you're going to get a much lower note, lower frequency, longer wavelength, lower note being produced. That's your Doppler shift. That's what it is. There is a calculation that goes with this. If you want to check out chapter 15, you can see the equation. It deals with your shift in frequency as it relates to and is proportional to the frequency the observer would notice or the frequency that the source is producing. We're not doing the equation. It's too complicated, especially for remote learning. So we're just going to talk about this conceptually. So we already talked about this a little bit. Where is the person going to hear the highest pitch? Where the waves are closest together. Where are they going to hear the lowest pitch? It's going to be where the waves are further apart. A longer wavelength means a lower frequency because wavelength and frequency from the last 2 weeks is still inversely proportional. So that's what we just talked about with those two slides. I broke it all down for you there. There's another nice little picture that kind of drives home the whole point, summarizes everything for you guys. So key takeaways. I'm going to leave this slide there for you guys. Hit pause. This is what we should understand conceptually. Again, no math. This is what the math would show you if you did the calculations. The book does a couple of practice problems, but the math is not something I'm going to request that you guys do. All right, so a couple more pictures. How much can sound change by? There are certain extents to which sound can change by as these objects continue to speed up and go faster and faster and faster. You'll notice that For objects that are stationary, you're going to get equal distances between all of those sound waves, compression to compression, so the same frequency forward and back. As it moves to the right, this gets to be a shorter wavelength, higher frequency, higher pitch note. So you're going to have a Doppler shift there. And then as they move away from the sound wave that they had previously made before making another one, because again, sound only travels at a certain speed. You can't speed it up or slow it down. It's based on the density of the medium it's in. So over here, you're going to have a much lower apparent frequency. But there is a point where if this vehicle is traveling at the speed of sound, you can actually get all of those sound waves out in the front of the object to bunch up on one another. And they create literally a massive wall of pressure. And that massive wall of pressure travels with the object. If the object goes faster than that wall of pressure that's what we refer to as supersonic. And this is what we're getting at, is shock waves and sonic booms. What are shock waves? What are sonic booms? Those are two vocab terms that we're going to talk about here in a second, but it all deals with objects, vehicles, which took us a while to be able to build and engineer, that can get close to that speed of sound, traveling at the same speed as those sound waves themselves. So what is a shock wave? A shock wave is going to be any sort of, just like it sounds, it is a wave. It's a wall of pressure, but it's a wave that moves faster through the medium than the local speed of sound actually should allow, which sounds counterintuitive. It doesn't sound like it should be a thing, but we see it all the time. All right, so right here with this little battleship, I think this is pulled from a movie or something. Doesn't matter. You can see the shock wave from the explosion in the water. It's literally that wall of pressure in the atmosphere is so strong that it's actually now displacing the water that is around the ship and moving it out of the way. So that's a really good visual of what a shock wave would be. Here's another good one. Some military guy set off a bunch of C4 or something like that. I don't know what it was. It doesn't matter. Right here along this wall, you can see all the dirt and debris and everything being kicked up inside of it, sure, but you can see right there where I drew the red line, you can see that distortion effect that that wall of thick air is going to have as it forces all of that air out of its way, right? The faster an object goes, the closer together those wavefronts become. At some point, you can reach a point where all of those wavefronts are literally overlapping one another. I've got two videos here that I think are really good. The first one deals with one of the original 1940s nuclear tests, 40s or 50s, that the U.S. I think it was the U.S. was doing. I don't know who was in the video. I assumed it was. Might not be. Doesn't matter. In the explosion, and I'm not going to play it here because I'd have to leave the whole presentation format and it'll screw everything up. But in this video, you guys will notice that the nuclear explosion goes off. You see the flash of light, you see the fireball, you can see the dirt getting kicked up on the ground around it, but it takes a while for the sound and the shock wave, the pressure wave, to reach you. Again, re-emphasizing that light travels significantly faster than sound. That's why you see flashes of lightning before you hear them. We'll talk more about the speed of light later. But it's a good video because you can see the shockwave come through, knock off the hats of a few of the people that are there. Watch it a couple times. It's only like a minute long. It's pretty good. And the next one is a volcanic eruption. You'll have to pardon the guy there. He's Australian and has some weird, I wouldn't say expletives because there's nothing inappropriate, but it's funny and you'll enjoy it. But again, it's the exact same idea. You see the volcanic eruption. You can actually, if you pause it and rewind the video a little bit, you can see it push the clouds out of the way. You can see it kick up the dirt, the shock wave that is, kick up the dirt along the side of the mountain as that shock wave travels outward. And then after that shock wave leaves the dirt and you see no more dirt getting kicked up, it takes a couple of seconds and then you hear the boom. You hear the sound. You finally get the wall of air that hits it, shakes the camera, and all that good stuff. It's a pretty good video for shock waves. Sonic booms are a little bit different. A shock wave is the physical wall of pressure, the overlapping of all of those compressions as they travel from point A to point B, usually interacting with things along the way. But sonic booms are the sound that we associate with those shock waves. So one is the physical feature, shock waves are the physical thing, and the sonic boom is the sound we interpret that shock wave as. Sonic booms are going to happen when, as these fighter jets, because very difficult to do this with cars on land. They do have cars that fast, but they're very difficult to find or even build or find a spot flat enough to where you'd want to go that fast. But with these aircraft, notice the faster they go, you end up getting these wave fronts. And at some point, you can get all of those wave fronts overlapping. And if you go faster than the wave that you produced, outrun the wave you produced, you would be what we consider supersonic. And at these supersonic speeds, you still get this overlapping region, but that overlapping region is now a cone. It's not a somewhat vertical or circular, semicircular shape of pressure that's traveling with you. Mach 1 is the speed of sound, 330 something meters per second. But when you exceed 330 meters per second, you're going to get that triangular shape that everyone is familiar with. There's a video right here that's going to talk about how this happens. Those cones actually follow that overlapping that you see down here, and it follows that little triangular shape. You can see it right there. This is taken from not directly on the side. There's video or parts of this video right here that will have it directly on the side. You'll see its conical shape, I suppose you should say. You'll see the shape of that cone there. In the video, they also talk about how and why those clouds form. The faster you're going, air cools and it doesn't hold moisture very well. It's why in the winter everything's super dry. Cold air doesn't hold moisture well at all. And so you get those clouds of condensation behind it. That's really all they're getting at there. But the cool part is that you can see them actually distorting the atmosphere and bending the air around them. It's not something you would normally think about, but you can watch it happen. And another cool video is a couple of British guys, again, blowing some stuff up. They actually set out some water balloons, set off an explosion and measure, because they know the distance between the water balloons. They measured the speed of the shock wave. I think it winds up being like twice the speed of sound or something cool like that. So not something we would be able to do even if we were in school together. But a really cool demonstration of how these walls of pressure don't even have to obey the speed of sound. The pressure wall itself, this shock wave, can travel faster than the speed of sound. It's kind of neat. So back to Doppler shifts. Doppler shifts occur whenever there is motion, either of the source of sound or the observer, or both. That gets way more complicated, but it works for all waves. It works for waves of sound. It works for waves in the ocean. There's another kind of wave that we're going to talk about next week that it will also work for as well. We're going to start it now, but we're going to talk about light a lot more next week. Light is just another wave. It's a different kind of wave. It's transverse, not longitudinal, electromagnetic, not mechanical. We'll talk about those things, but because it's also a wave, you can get Doppler shifts in light. Why don't you notice Doppler shifts in light as easily as you do with sound? It all comes back to relative speed. If you're moving at 33 meters per second, which is like 70 miles an hour, something we've all done at some point in our lives, you're moving at about 1% the speed of sound, which is enough. 1% is enough to screw with that frequency enough for us to hear a difference. You don't get the chance to get anywhere close to 1% the speed of light. You'd have to be traveling to get at 1% the speed of light, 300 million. You'd have to be traveling at 300,000 meters per second, which is faster than any man-made object has ever achieved, if I'm not mistaken. If I am mistaken, then 1% is probably our cap, and it's probably one of our satellites that we launched out in space thousands of years, or thousands of light years away. Not light years, sorry, thousands of miles away. Anyways, I think Voyager 1 and Voyager 2 are traveling a couple, I don't know, 10,000, 20,000 miles an hour. I think that would be the closest we get, and I'm pretty sure that's nowhere near 1% the speed of light. Anyways, so that's why you don't notice it in light. In your own, I guess you could say, perspective, what you've been exposed to personally. We do see it all the time in the world of astronomy. So we're going to stick with the visible spectrum here. You guys should all be familiar with the visible spectrum. You remember Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet, whatever indigo is. We'll talk about cyan a little bit later. That'll be one of our last weeks. But we're all familiar with Roy G. Biv. What I want you to see here, not that we're going to have to do any math with it. There's no math this week, which is nice, except for maybe old stuff just to keep you fresh on your wave equations, is that light has wavelengths. 700 nanometers is the approximate wavelength of red light, and we can observe violet light at around 400 nanometers in terms of a wavelength. That means the frequencies are different, the properties of those waves are different, and it's actually really interesting. It turns out the only difference between a violet photon of light and a red photon of light is literally how quickly it's vibrating. Its frequency, its wavelength. That's the only difference between the two of them. That being said, that means that we can actually observe these Doppler shifts in light as well, if objects are moving fast enough or are far enough away from us in order for that to be a thing. That's the catcher, is they've got to be super, super far away or traveling super fast. I remember in college, I did one of the problems that we had to do freshman year of physics was a frequency change problem where you had to figure out how quick you had to be driving down the road for a red light. Let me go back. Can I go back? No, it won't let me. Cool. For a red light to appear green, to have that much of a Doppler shift. Turns out it was like a couple 100,000 miles an hour, so it's completely impossible. But the same principles apply for light as they did for sound. As that wave source approaches you, frequency increases. As the wave source leaves you or moves away from you, it decreases. But that also means that you're going to have changes in color. Right? If your frequency increases, that means your wavelength will get smaller. And so if your wave source is approaching you, you're going to get a more blue shifted color. And if the wave source is leaving you, you're going to get a more red shifted color. How do you know what the color should have been originally? We'll talk about that next week when we talk about atomic emission spectra and stuff like that, how light is generated. But just know for now that if the frequency of light increases, the color becomes more blue, violet. We literally call it a blue shift in astronomy. And if the frequency of light decreases, it's moving away from you, we call it a red shift. That term red shift might be familiar to some of you guys who are familiar with astronomy. We're going to talk about that briefly here now. How do we know the Doppler shift happens in light if it's too fast? We take a look out into the universe. In the early 1900s, a lot of scientists were, telescope technology got a lot better. We had different ways of actually being able to measure and observe light that was coming from distant reaches in the universe. And we noticed that there are significantly more red tinted stars in the universe than there should have been because there was that red shift. We came to the understanding and proposed the hypothesis, this is what Edwin Hubble did for us, that things are actually moving away. The universe is expanding, it's getting further and further apart, everything is getting further apart from each other because we're observing red shifts in a lot of that light. And again, this is the same visual we had from the beginning of the notes overlapped with light. You'll notice over here on this side, you've got your blue shift. Because the frequency is getting higher over here, you're going to have your red shift because the frequency is getting lower. It's a much longer wavelength. The primary frequency of light that we were observing is longer than it should have been. We'll talk about how we knew what it should have been next week. This is what we called red shifts. The main idea behind all of this was simply that this is our evidence for the Big Bang Theory. Now, I like to always come back to what we talked about at the beginning of the year. Theories are well-supported hypotheses, nothing more. At this point, we have a collection of evidence, and this actual TED Talk right here is going to mention a lot of it. It's short. It's one of those quick 5-minute TED videos. But they talk about Big Bang. They talk about Doppler shifts with light and a few other things. But the key factor there with the Big Bang Theory is that this is just evidence that supports it. There's only two ways, really one way to ever know whether or not this theory was factual. I guess two. And that would be to go back, build a massive time machine, go back to the beginning of the universe and watch all of it happen, or, wind up passing away and talk to whatever creator might have been responsible for it. That's the only way we'd know whether or not a theory is valid. What a theory does for us is it supplies tons and tons and tons of evidence that the universe is accelerating. And this video right here is going to walk you through that with much, much better visuals than I ever could. How we know the universe is expanding, how we know it's accelerating in that expansion. They talk about dark energy. being the reason the universe is expanding and accelerating. Basically, the further away we look, the faster those objects are moving away from us, and the closer they are, the slower they're moving away from us. We don't know why, so we call it dark energy. Doesn't mean it's mysterious or evil or malevolent. It's just that we have no idea what it is, but we can observe things moving away. And that's all that theory is trying to state. And then the last link right there is a review of literally everything we've talked about so far. I know this was a 25-minute video. I was trying to keep it shorter than that. Things happen. But this is a quick review of all of Doppler and light. I checked all these links. All the links work. If you have any questions or concerns about any of this Doppler shift stuff, again, this is an entirely conceptual week outside of all the wave equation stuff with wavelength and frequency that I'm just going to have you guys practice a little bit of. This should be a easier week in terms of mathematics. Yeah, email me if you have any questions, concerns, make a post on Edmodo. Some of you guys were just making comments on the homework assignments that you submitted, but I'm not seeing those until the end of the week. So if you have a question that you want answered desperately, please email it or post it to the whole class or something along those lines so that I can address it right away. That's about it. Get working on assignment 2, which is a conceptual breakdown of all this. Those answers will be up by Thursday. And yeah, miss you guys. See you around.